Today is the last video on chapter 18. We're going to start out with a different kind of reaction. So this whole chapter has been about electrophilic aromatic substitution. You have an electrophile come in and be attracted to the benzene ring. This next type of reaction we're going to talk about is the exact opposite. This is nucleophilic aromatic substitution. So in this case, you're going to substitute a halogen that's already on the benzene ring by some sort of nucleophile. So you can't start out with just benzene, you have to start out with a benzene that has a halogen on it. And right where you have the halogen, you're going to stick a nucleophile on. There's two different possible mechanisms for this, and there's support for both of them. Neither mechanism is an SN1 mechanism or an SN2 mechanism like you've learned before. These are totally different. Our two types of mechanisms are either addition, elimination, or elimination, addition. And this just talks about what order these things happen in. So with addition elimination mechanism, that's the one we're going to talk about first. The electron withdrawing group in a para, it has to be in a para or ortho position to your halogen. So you can't just have a benzene ring, you have to have an electron withdrawing group also. Because electron withdrawing groups activate the ring for nucleophilic aromatic substitution, it's the exact opposite of electrophilic aromatic substitution. So if you want this to happen, you're going to have a strong nucleophile. So, strong nucleophile, this is what's coming into your ring. These would be things like OH or NH2-. Sometimes you can use neutral nucleophiles like NH3. Let me give you an example of how this works. Because first you have to add the nucleophile to make a resonance stabilized carbanion, and then you eliminate the halogen leaving group. This is why it's called addition elimination. Here's the mechanism. So you've got your benzene ring. You have your electron withdrawing group. That's what the W stands for. And your halogen. So the nucleophile is going to add to the carbon where the halogen is. If it adds there, we have to break a bond. The easiest bond to break is this pi bond. Those electrons go out on the carbon. Our intermediate looks like this. Here's your withdrawing group. Here's your halogen. Here's your nucleophile. And what happened? We removed these electrons and we put them out here on this carbon. So you have a carbanion right here. The resonance structures for this look like this. So you can have the electrons move over here where that electron withdrawing group is. That's what stabilizes your benzene ring. You can also move them this way. So they are right here, ortho to your group on the other side. Then what happens in the last step is that these electrons go to reform the aromatic ring and the halogen leaves as a leaving group. So you end up with a nucleophile substituted exactly where the halogen was. More electron withdrawing groups increase the reactivity. So if you have extra electron withdrawing groups or they're stronger electron withdrawing, it's going to stabilize your carbanion. And the increased electronegativity of the halogen increases your reactivity. So fluorides are more reactive than chlorides, which are more reactive than bromides. This is the halogen that's on the benzene ring. So anything that pulls electron density out of that ring makes it go better. And para or ortho electron withdrawing groups are more reactive than if you have meta with electron withdrawing groups to the halogen. So that's the first possible mechanism. Our second mechanism is called elimination addition. So here you have elimination happen first, and then you have addition. Our intermediate is called benzyne. So it looks like benzene, only it has a triple bond in it. You don't need electron withdrawing groups for this kind of mechanism. You use forcing conditions, so high heat and pressure force this reaction to go. You're going to substitute on the carbon directly bonded to the halogen, and you're going to substitute on the carbon next to it. And I'll show you why if we look at the mechanism. Here's your, that didn't turn out well. Let's try again. Okay. Here's your benzene ring that you're starting out with. Has a halogen on it. There's a hydrogen here. A base comes in, right? Remember, you have a nucleophile that can also act as a base, and it removes this hydrogen, which then puts the electrons here on this carbon. These electrons can then go and form a triple bond here, which makes this halogen leave. This is your benzyne intermediate. It's extremely unstable. You can see that the angles are not correct, that you have a triple bond messing with the aromaticity, etc. And so once you've formed that benzyne, then your nucleophile can come in from either side. It can come in from the top here, or it can come in from the bottom. And these electrons go back off. They're here, and then water that's in solution can protonate. So these electrons can now be protonated by the water, and you have regenerated your benzene ring with a new substituent, an OH instead of a halogen. So this elimination addition mechanism puts a substituent on that carbon directly bonded to the halogen, or the one next to it, because you can attack the benzyne from either side. That benzyne is just a sigma bond formed by the overlap of two sp2 orbitals, and then one pi bond is normal. It's formed by the overlap of two p orbitals, and your other pi bond is formed by the overlap of two sp2 orbitals. So super unstable, but it forms as an intermediate quickly to get to the product. So in this particular instance, we're going to start looking at what we can do with side reactions of benzenes that we've already substituted, so things we've put on them. So first of all, we have this particular reaction. So if we have an alkyl group on our benzene ring, and there is a hydrogen that is next to the on the carbon next to the benzene ring, we can use radical conditions. So Br2 and light or heat. Or we can use NBS with light. Or we can use peroxides. Remember, all of these were options in our radical chapter, and they're going to give us a bromine on the carbon right next to the benzene ring. So as long as you have a hydrogen there that you can substitute, that bromine can go on. It won't work with tertiary carbons, but it will work with primary and secondary carbons. It works because that benzylic radical is resonance stabilized, just like allylic ones were, if you remember back in the radical chapter. It can be stabilized just like allylic radicals. So, if you use Br2 and FeBr3, you're going to brominate the ring. If you use Br2 with light or heat, then you're going to get the radical reaction of the side chain. The nice thing is then once you put a halogen on, you can use that benzylic halide as a starting material for other reactions. We can also oxidize and reduce substituted benzenes. So the mechanisms for these are complex. You don't have to learn the mechanisms. You should just learn the reactions. So if you have an alkyl benzene, again, same restrictions as before. So there has to be at least one hydrogen on this R group, on the carbon coming right off the benzene ring. If you add potassium permanganate, the product every time is benzoic acid. So it cleaves the whole alkyl group and you end up with benzoic acid. Doesn't matter what the alkyl group that is that you start with, as long as it has a hydrogen on the carbon next to the benzene ring. If you have more than one alkyl group, every one becomes a carboxylic acid. And if there's no benzylic hydrogen, there's no reaction. We can also take aryl ketones to alkyl benzenes. So you'll recall that if you do Friedel-Crafts alkylation, sometimes you can end up with substitutions. However, if we do Friedel-Crafts acylation and then reduce our product, you can reduce it to an alkyl group. You have the alkyl group right where you want it. So here's our reduction. That's one possible combination, or the other possible combination can be hydrazine. If we use this bottom one, it's called the Wolff-Kishcher reduction. This top one is called the Clemmensen reduction. Both of them do the same thing. So it's going to replace both CO bonds with CHs. So you can make alkyl halides directly if there's no rearrangement possible, or you can use a two-step if rearrangement is possible. The last one I want to talk about is reduction of nitro groups. So there are a few ways to get NH2 on a benzene ring, but it's complicated to add it directly. And so you easily know a way to put a nitro group on a benzene ring. And you can use our same reducing agents that we've been using before, H2 and palladium on carbon, or we've got some other options, iron with hydrochloric acid, or tin with hydrochloric acid. All of these options will take a nitro group and reduce it to an amine. So, for example, if I wanted to take benzene and I wanted to make metabromoaniline, what I could do would first be add HNO3 and H2SO4, so sulfuric acid and nitric acid. That would put an NO3 or an NO2 on. Then I could add Br2 and FeBr3, and that will put my Br on, and it will add in the meta position because NO2 is a meta director. And then I could do a reduction with any of those reagents shown above. and I could reduce my nitro group to an amine. So this is one of our first examples of a multi-step synthesis. And this would happen a lot in aromatic chemistry, where you need to add more than one group on, and you need to decide which groups to add on and in what order, and if you have to change any of them. So here's an approach to it. If I'm doing multi-step synthesis with aromatic rings, the first thing I want to do is look at my functional groups. And I want to say, can I put those functional groups on directly? Or do I need to put it on as something else and then transform it? So direct or indirect? The second thing, after I've decided what functional groups I need to put on, is to look at the original groups that I need to add. So if I'm going to transform something at the end, that's okay. But I need to look at the original groups that I need to add. And are they ortho-para-directing or are they meta-directing? So what do I need to put on first? So are they ortho-para-directing? Are they meta-directing? The other thing I would want to think about is when I transform a group. So if I need to transform a group, like an NO2 to an NH2, do I want to do that after the first step, after the second step, after the third step? Because that's going to all of a sudden change which way that functional group is directing, whether it's directing ortho-para or whether it's directing meta. So after each step, I would look and say, okay, where do I need the next part to go on? Where do I need the next part to go on? And can I do it in the way that I've done it, or do I need to back up a couple of steps? That's the end of Chapter 18. We'll see you around the corner in Chapter 19.